Now, I'm going to go through two methods to go through and factor this. You can choose whichever one you like, and I'll briefly explain them before actually going through them. So, for factoring it, we can see that this has three possible factors. We have 1 over s, 1 over s plus 1, and then 1 over s plus 1 squared. And so the reason why we differentiate between s plus 1 and s plus 1 squared is A, if we were to expand this, we would get a power of 3, so you want to have three separate factors. B, it's because you might not if you don't have that, then you might not actually be able to get a complete solution. And so sometimes one of these will be equal to 0, the coefficient. However, oftentimes one of them has a value such as 1, 1/2, or some numerical value. So it's always important just to remember to have them here. Now this is where I'm going to branch off into the two methods. So the first method is just brute force. What you're going to do is you're going to take the factors that aren't present in the fraction, multiply by the top, and then add all the tops, equated equal to 1, and just brute force using algebra. The second one is using limits. So for the limit one, what we're going to do is for different zeros, so for example here it's 0, here it's -1, we'll actually take the limit of the overall function at that point, removing it. Now, because we have a repeated one here, we won't be able to do the middle factor, so we'll have to only do it for the first and last one, so we'll be able to determine A and C from this, but B we'll have to determine using algebra. So, algebraically all the way through, we get A times s plus 1 squared plus B times s squared plus s, which is s times s plus 1, plus cs. So now when we expand this, we get as squared plus 2as plus a plus bs squared plus bs plus cs is equal to 1. So what we're going to do is we're going to isolate for the different powers of s. So for s squared, we get a plus b, and that has to be equal to 0 for the coefficient, because in the coefficient here, we don't have any s squareds. So you could also view this as 0s squared, if that helps. Then for s, we have s times 2a plus b plus c is also equal to 0. And then for 1, we have just a. So we know that a automatically is going to be 1. And then from here, we have b is equal to -a. So we know that b is equal to -1. So for c, what we're going to do is we're going to plug both b and a in, so then we get 2 minus 1 plus b plus c, is equal to 0. So c is also equal to -1. Now, to show how we can get both a and c using limits, what I'll do is I will take 1 over s plus 1. What you do is you have, so a, for example, the 0 for this factor here is 0. So what we're going to do is we're going to take the limit as s goes to 0 of everything except for that factor from the original one. So it's 1 over s plus 1 squared. So when we do that, we get 1 over 1 squared, which is equal to 1. So that's it. And then for c, we get the limit as s goes to -1 of 1 over s. And again, the reason why we didn't do this is because if we were to, we always want to go with the highest power if you ever have repeating factors. And the reason for that is if we were to do this and we were to remove one of the s plus 1s, there'd still be an s plus 1 in the denominator, resulting in 0 in the denominator, which is never fun to play around with. So, we have -1 in that, which gives us -1, which is our c. And so from here we can solve for a b, just say using this equation here. And so now if we're actually converting it back, what we're going to do is we're going to put the coefficients back into the factorized form and then simplify. So when we do that, we get the inverse Laplace transform of x is equal to the inverse Laplace transform of 1 over s minus 1 over s plus 1 minus 1 over s plus 1 squared. And so now, this equates to x of t is equal to 1 minus e to the negative t minus e to the negative t times t. And that is how you solve differential equations using Laplace transforms. So now just another one, just to confirm our knowledge of this. The key thing to remember regarding this is if ever you see a differential equation that looks absolutely baffling to you upon inspection, you just don't know what to do at all, normally the Laplace transform will be able to simplify the actual solving process. And oftentimes for non-homogeneous differential equations, so where it isn't equal to 0 on the opposite side of the differentials, it's key to remember to use Laplace transforms because they'll simplify everything. So now we have the second derivative of y with respect to t minus 3 is equal to 0. And again, initial conditions are y of 0 is equal to y prime of 0 is equal to 0. So, now what we're going to do is we're going to apply the Laplace transform. So recall the Laplace transform of y double prime is equal to s squared y minus s y of 0 minus y prime of 0. And again, these two are both 0. And then the Laplace transform of 3 is equal to 3 over s. And Laplace transform of 0 is just equal to 0. So we get s squared y minus 3s is equal to 0. So what we're going to do is we're going to multiply everything by s. So we get s cubed y, because clearly s can't be 0, so we don't have to worry about it as it's already in the denominator. So we get s cubed y minus 3 is equal to 0. So then y is equal to 3 over s cubed, and then we take the inverse Laplace transform of that. And that gives us y of t is equal to t cubed over, let's see, t squared over 2 times 3. And again, the reason where the 2 came from is because of the definition for polynomials. So say you have Tn, the Laplace transform of that is going to be n factorial over s to the n plus 1.